Hi there, I'm Prof Joe, and this is part of my AI-Tutored lecture on measurement technology. And today we're going to talk about the basics of alternating currents and voltages. So, what do we think of when talking about alternating currents or voltages? Normally we think of something which has the form of a sine or cosine and looks quite straight and similar. To get that into the right picture, normally we don't have those perfect forms. We don't have perfect sines or perfect cosines when getting some power or current for our household or anything like that. So is that assumption justified to reduce, to think about sines or cosines when talking about alternating currents? That's the question right now. And for sure it is. The reason for that is quite simple. I think you know all about Fourier transformation and that stuff. And you know when adding up several sines or cosines, we are able to build up any arbitrary function we want to, actually. Something like a sawtooth or even more arbitrary functions. That's nice. That means for our simple electrical circuits, only including ohmic resistors, capacitors, or inductances, we can assume that we have linear differential equations for those electrical circuits. And for that reason, we can assume when adding up as many sines or cosines as we want to, those will also solve those linear, simple differential equations. That means looking only at sines or cosines, or only looking at one sine or one cosine function or one exponential function with an imaginary exponent is enough, because the sum of them, summing them up won't change anything to the system inherent, meaning won't change the solution, the way to solve those linear differential equations, and by that not change anything in the basic behavior of our alternating voltage or current. And that results in the fact that it's enough for us to deal with sines and cosines and very simple exponential functions with only one exponent. That makes it much more easy to talk about alternating voltages and currents, because that picture of a sine or cosine is justified. It's legitimate to only talk about a sine or cosine function for the cases we are looking at. Meaning there are some nonlinear equations out there for electrical circuits and so on, and for those it's not really justified, but for those there are other problems, and it's very much more specific than we want to talk about the stuff. Meaning we want to measure an alternating current, an arbitrary function over time. And that is right away possible by just using our oscilloscope or our standard measurement devices, because they only bring along some capacitance and some ohmic resistance most of the time. And for those resistances, for those complex resistances, it's enough to talk about sines and cosines and to use an exponential function with an imaginary part. That brings me to the next thing we need to know about, and those things we need to know about for alternating currents are imaginary functions, like a function like that, which denotes the Euler equation, which connects the exponential function having the imaginary number. Sometimes it's denoted I, we denote it with a J. That's the, for those textbooks I read, talking about electrical topics, they most of the time use J instead of an I. Being a physicist, I was used to using an I and not a J, so we won't care about that. That is our imaginary number, and that is connected to the cosine and the sine function as I denoted here. And so that is the thing we can simply use as picture, as model for any arbitrary function out there. Because we could sum up dozens, hundreds of those functions and won't change the system inherent. And so it's enough to look at one function. Perhaps not knowing the frequency, the circular frequency, meaning perhaps thinking about the system for different frequencies at the same time, but just looking at one function. That makes it much more easy. That makes it possible to have all those curves, amplification curves for filters and all the other stuff we can look at just dealing with the parameters of the circular frequency and the phase shift. Not dealing with the whole set, with the whole sum of all functions or with an arbitrary function, which would make calculations much more difficult. We don't need to do those difficult calculations. Okay, coming along with that imaginary stuff are capacitors and inductances, meaning those are resistances with complex numbers in its value, in its quantity, which only come into play when having alternating currents. Think of a capacitance looking from the point of view of a DC current or a DC voltage. A capacitance is nothing more than a resistance with a value of infinity. Meaning, which is just a disconnection between two circuit parts. So for a DC current, that means no current flows at all. But for an alternating current, that is not the case, because the alternating current always swaps around, and so that capacitance gets loaded and deloaded and so on. And so it takes a massive influence on the behavior of the alternating current itself. And for the alternating current, that is not a restriction for no current to flow, because only a small part of the current flows all the time in both directions, and so loads the capacitance and deloads it again, and so on and so on. So for our complex calculations, we need complex resistances to get hold of those sines and cosines, to get hold of all of those alternating currents. Great. That's enough for the basics. Important thing again is we only need to talk about sines and cosines, and don't restrict us from talking about arbitrary functions. That's important, because when using an oscilloscope for a measurement, we most of the time want to record arbitrary functions. And now the question arises, we need to look at that system and that function. We don't even know about the form in respect to time. And so can we talk about that function? Yes, we can talk about it, because we just are able to talk about sines and cosines, and that arbitrary function can be built up of a large sum of those simple sines and cosines. And so all the behavior in respect to circular frequency or to phase shift also hold for the arbitrary functions. When we are not able to talk about that arbitrary function as it is, we are able to do a Fourier transformation. Meaning to get all those sums, to get all the frequency parts of our arbitrary signal, and then we are very directly, very specifically able to talk about the behavior of that arbitrary signal. Meaning, if there's a sharp edge, high frequencies occur, and those high frequencies might be cut due to some capacitance or something like that. When there's a very low slope, we know there are very low frequencies in it, and perhaps that has something to mean. Perhaps you want to filter some certain frequencies because there are some higher frequencies we are not interested in, and so on and so on. And all of that stuff is legitimate. We can do it because talking about sines and cosines is enough. Having said so, this is the end of part 1. Hopefully see you again next time.